DC motor takes in AC voltage, converts it to high voltage DC, and runs the motor that way. Brushless motor, permanent magnet motor, all these are the same things that are all integrated. So permanent magnet, these blue magnets, those are inside of the motor. What's different, lots of times you see a motor, it has a shaft coming out of it, and that's what you put the wheel on. Ours, it's an external rotor motor, we call it. So this rotor on the outside of it is what rotates. So that whole part rotates, the wheel attaches to that, and it spins that way. Everything that we sell is factory balanced and factory tested. So nothing leaves our facility without 100% testing and 100% balancing. It has alarm relays built in. It has locked rotor protection. So one thing that's really cool with our fan is if it's in a locked rotor condition, something's blocking that rotor, prevents it from spinning, tries to spin, realizes it's locked, waits 3 seconds and tries again, and just keeps doing that. In the meantime, it also sends out an alarm saying, hey, I have a locked rotor, something's wrong.
So it'll do that infinitely?
Infinitely until it's cleared. What's nice is you don't overheat the motor because it's not actually ramping up. An AC motor, what else is out there in the market, it just keeps on trying to clear that condition and just over torques. And then eventually the way it stops is it overheats and a thermal break happens, and then it cools down and then just immediately goes right back and starts trying again. So it'll hurt the lifetime of it.
Is there a brake inside of this motor as well? So
there are thermal overload protections, yeah. Okay. So that's all in the motor as well, but it's not like the dielectric metal switch. It's always integrated with sensors. So it's done by sensors, not by an actual opening of an alarm.
So I'm thinking about if in our product, for example, a motor fails, you have backflow through a motor, and it's like trying to spin the other way. Is there a mechanical break?
I do get to that. So
okay.
No, it's a great question though, because with an AC motor, what will happen is say that you have 4 AC motors on one drive, one of them fails and starts spinning the wrong way. It generates power, feeds it back into the VFD, and then can fail the VFD. Our fan doesn't do that. What it actually does is it generates the power. The electronics realize, hey, I'm running the wrong way. There's an electronic brake inside the motor, and it dissipates all that energy. And it'll just keep doing that. So that's how it prevents it from getting backfed into the grid.
Nice.
So EC, everything that you see on the right is included on the left. So it's in a nice compact package. So there's no slip losses. You don't have to worry about synchronous speeds, up to 95% motor efficiency. Operation down to 8% speed. So usually with an AC motor and a VFD, 30% is about as low as you get. And the problem is at 30%, that AC motor is horribly inefficient. So we'll get to that a little bit too. Identical performance at 50 and 60 hertz. So if you're shipping something to South America that has 50 hertz power, you're gonna get the same exact performance as if you plugged it in here. AC motors do have 2 different performance curves at 50 and 60. You could use 0 to 10 volt, 4 to 20 milliamp, PWM. There's so many different ways to control it. Matt talked about this, smaller size in the unit, you save space, and your coil gets much, much better coverage. So this is an old style motor with the belt, and you can see there's high velocity areas, low velocity areas. Your coil's not optimized. With the fan array, Matt also mentioned this morning, you get much, much better optimization. So you don't have high velocity areas and low velocity areas. It's much more laminar flow through the unit. So you don't need shielded cablings. You don't need any sine filtering. It's all built in. Motor protection's built in. Shaft grounding kits aren't needed on EC motors. The shaft itself is isolated, so you don't have to worry about shaft grounding kits. Don't have to worry about a VFD. So the bottom line is simple and safe, and it's maintenance free in the field. Once you install it, there's no maintenance until the fan fails.
What's the field fail rate currently?
As far as, so this is actually the lifetime side.
Okay.
So, it's a good question.
What about piezo ring or flow measurement?
Flow measurement, piezo ring, good question. So it's all available on the EC motor. It's available at a selection stage. I recommend single tap. Normally, because EC motors are pretty small, you're using small diameter wheels. Piezometer rings are a pain, they break in shipment. There's lots of issues with them. Whereas single tap, it's much more sturdy, and you're still gonna get, its accuracy is about 5 to 7%. The piezometer ring is like 3 to 5%. So you're really, you're not really losing much accuracy for the amount of headache that you're saving.
Yeah, no, it just wasn't on the slide.
Yeah, so it is available. Yep. So we calculate our lifetime by L10. So what L10 means is that's the number of hours that 10% of the motors are going to fail. So it doesn't mean everything fails at that time. That's when 10% would fail in hours. So on average, L10 of 100,000 hours for air handlers. So it's 11.4 years. This is because fan's dynamically balanced. So the bearing is going to be what fails, but we're balancing it to make sure that we get the most life out of it. If the bearings,
10-year warranty, right?
we don't offer a 10-year warranty because we don't have to. It's going to last you.
It's worth an ask.
All of it's
Reward, yeah.
all of it's end of line tested, and once it's installed, it's maintenance free. So how about an AC motor with a VFD? Typical life of a VFD, 7 to 12 years. Typical life of a 5 horsepower AC motor, 12 to 17 years. But this is the key. That's based on nameplate voltage and frequency. If you're putting an AC motor with a VFD, you're no longer running at nameplate voltage and frequency. You just dropped your lifetime substantially. So it's also going to drop if you're not properly balancing it, if you have to do shaft grounding kits and you're not installing it correctly, if you're not using shielded cabling, and if the VFD is not programmed correct. This is what the perception is on EC motors and having to replace them. You have to replace the entire assembly, so it's expensive. It's long lead time for EC motors, so you got to wait a long time to get them. This backdraft thing, actually we covered that already, of how if it does fail, it'll actually recognize it, do the power dissipation. The perception on AC motors is, hey, they're in stock, I can get it quick, I can replace the motor only, I could leave the wheel and VFD, so I'm saving money, and it's really, really simple to install. So what you think happens when an AC motor fails? Motor's failed, you remove it, so you leave the impeller, you leave the VFD, you put in the new motor, and everything's happy. The reality is, the motor fails, you remove it, you still leave the wheel, you still leave the VFD, you replace the motor, but now there's a problem. That motor's not balanced to that wheel anymore. So you got to get a balancer out to the site. Nobody is getting balancers out to the site for the most part. Very few people are doing this. So that motor now is going to be, lots of times first motor that fails is the second motor that fails, because that wheel's not balanced and you're wearing out that motor bearing. Also, because the VFD's life is about the same as the motor, best practice would be to do one service trip, replace the VFD as well, which is more cost. Now you got to get a programmer out there as well. And to get a balancer out on site is a lot of money. That is not a cheap thing to do. What happens when an EC motor fails? So it's failed, you remove it. Normally, as we mentioned, there's some redundancy built into these fan arrays that Q-PAC's selling. They're not selling one fan, they're selling a few of them. So if you have an M+1 system, you're getting 100% of your cooling for that building. Even if you don't have an M+1 system, say you have 4 fans and one of them fails, you're still getting 75% of your airflow. So you're still getting a lot of cooling, you're just not getting the full cooling. You replace the fan, it's already been pre-balanced, pre-programmed. All you have to do is return that initial wiring and it's done. You're all set. You can walk away, you're going to get the full life out of that fan. The reality is replacing an EC motor is actually going to be cheaper than replacing an AC motor. When you factor in all the costs, that the fact that you have to get now a third party out to the site, it's going to cost you more money. The lead time risk can be mitigated by using standard parts. So what I mean by this is, if you have a building that has 10 air handlers, select the same fan if you can for all 10 air handlers, and then tell the building owner, hey, why don't you keep one on the shelf, an extra one. Then when one fails, he has one on the shelf, he replaces it, and he orders a new one for the shelf. You don't have to worry about lead time then. The reality on replacing AC motors, we saw it in the videos earlier, they're very, very difficult to replace. They're heavy. Sometimes you got to take down walls. Like, it is not a simple thing to replace this AC motor. After it's replaced, you got to get a balancer out to the site. People aren't doing this. Since most aren't getting rebalanced, and I've heard this from many OEMs, first fan that fails lots of times is their second service call as well. It's the second motor that also has failed. And I mentioned how the best business practice would also be to replace the VFD. How much weight are we actually saving with EC motors? 11-inch, 1.5 horsepower EC motor, saving about the weight of a bowling ball. 5 horsepower, 12-inch, it's like a bag of sand that you would put down for a flood water. This is where it gets interesting. So 5 horsepower, 16-inch, you're up to a lazy boy recliner. So as we said, you're not putting one fan in, you're putting 4. So now you're talking 4 recliners, a living room set that you're taking out of the unit. And this 7.5 horsepower 18-inch, that's a canoe. So once again, now you could be talking 4 canoes that you're pulling out of the unit. That's a lot that you have to carry up and down stairs. Anybody want to carry a canoe up a stairs? No. It's way, way better to use the EC product. It's one of Q-PAC's great features is it fits easy. You can easily move it throughout a building. So comparing kilowatt to horsepower. So we always give a number in kilowatt. Kilowatt is what you see there. It's the full fan assembly, what you see on all the shelves here. Brake horsepower is the power to spin that. That's it. Doesn't factor in your belt, your motor, your drives. All that's not factored into your brake horsepower. The reason we give kilowatt is because we can. We have this full assembly. And if you notice on your electric bill, they don't charge you in horsepower. You care about the kilowatt. The reason the traditional solutions give you horsepower is not because they're trying to be difficult or sneaky. It's an AC motor guy selling an AC motor. He can't give you kilowatt. He doesn't know what else you're putting with it. So he has to give you horsepower. That's his only choice. But if you aren't smart in figuring out how to convert between the two, because you can't just go into Google and say, hey, this is my brake horsepower, how much kilowatt is it? Not going to work. This is something that the market needs to be educated on because we get that a lot. So I had a customer that called me up and said, John, how come your EC motor that you told me is more efficient is way more power than my AC motor selection I just did? You're full of crap. I said, all right, send me over the info. Let me take a look at it. So it's a 40,000 CFM unit. He took our kilowatt numbers, converted it to horsepower, compared his brake horsepower he was getting, and you can see his AC VFD was lower power than our EC motor. But I told him, you're not doing it right. You're only factoring in the power to drive that wheel. You're not factoring in your motor efficiency. You're not factoring in your drive losses, any belt losses. This was a direct drive, so there was no belt losses. But still, you're not factoring in all the stuff downstream, the bearing system. And there's another part of this. If you have a 93% efficient motor and a 95% efficient drive, that's at their peak points. The peak point of the motor is not going to match the peak point of the impeller and match the peak point of the drive. It's just not going to happen. But I'm even giving them all that in this calculation. And I say, you know what? I'll give you a 93% efficient motor and a 95% efficient drive, and I'm still more efficient. So that's at 100% speed, which is going to be that peak performance of an AC motor. But what happens at lower speeds? So this is measured data for us down to 50% speed. What we find is our motor plus our drive efficiency is 75.17%. Measured. Tested data, not calculated. This is actually the picture of the test that I got that from. So you can see it was on the lab chamber, 7.5 horsepower motor. So what I did, I gave AC and VFD as much credit as possible. Instead of comparing it to a 7.5, I compared it to a 10 horsepower premium motor. The higher horsepower, the more efficient the motor is. So I'm giving them that benefit. I'm going to consider 50% speed, but speed is cubic, or power is cubic to the speed of the fan, sorry. So it's an exponential curve, which means 50% speed is not 50% load. 50% speed is 12.5% load. Also, another thing to consider is almost never are you operating at that 100% speed point on an AC motor, because if you have a brake horsepower of 7.4, you're not selecting a 7.5 horsepower motor. That's too close to that maximum. So you're going to select a 10 horsepower, which means you're already derating it, so you're never going to get that high efficiency point. But I went to usenergy.gov, got some curves, so I found out the motor, 10 horsepower premium efficiency motor at 12.5% load, 68% efficient. So already our EC motor, including the drive, not including the wheel in this case, just motor and drive, is more efficient than the AC motor at 50% speed, not including the drive. So we're already 7%. Now what about the drive? Drive at 12.5% load is 83% efficient. So now we're saving almost 20% in efficiency just based on the technology alone. Our wheel is also more efficient than their wheels. So you're going to save way, way more than 20% at 50% speed. It continues to grow as you go down in speed. I mentioned we can go to 10%, they can go to 30%. That gap just gets higher and higher as you continue to go down. Also, air handlers are designed for the hottest day of the year, full speed, full air conditioning, never runs there, right? Very rarely are you running at that 100% point. So they almost always operate at part load, where this EC fan is really going to have a huge gap on an AC motor. Another way to do airflow control is, I said, you're not running at 100%. So say that you have 8 fans and you want 50%. Some people turn off 4 of them. They get 50% speed, 50% airflow. But as I mentioned, power is cubic to the speed of the fan. So if you do that, you're actually drawing a lot more power than if you ran all 8 fans at 50% speed. But there's more advantages than just power. So if you have 8 fans and you turn off half of them, you save 3 decibels in sound. But if you have 8 fans and you run all of them at 50% speed, you save 15 decibels. That's tremendous sound savings. Also, the L10 life that I was talking about before, that's also exponential to the speed of the fan. So if you run all 8 fans at 50% speed, you're going to get much higher lifetime than if you run 4 at 100% and 4 that are off. So it's another way to get longer life out of your product. So there's 3 advantages. You get power savings, you get lifetime, and you get sound savings. All right, so now going through some EC rumors and myths. So EC motors have a higher capital cost. Say that's true but misleading. If you just compare the price tag to the price tag, then yeah, it's probably a little higher. But if you think of an AC motor with the VFD, plus the wiring, plus the space, lots of times EC is going to come out cheaper. There's a reason large OEMs are using us. They've done this calculation. They know that it comes out cheaper. EC can't do high static pressure systems. False. We have high kilowatt motors. We can get over 10 inches of static, but this used to be true. 5 years ago, 3 to 5 inches was about what EC motors could get. So they were right. They're just wrong now. EC motors can generate high harmonic distortion. There's a whole different session on it, so if you want to hear about harmonic distortion in depth, there's other guys talking about that. But the bottom line is, we have the same solutions and same numbers, can reach the same numbers that a drive can. So an ultra low harmonic drive, we can meet all that. All right, EC motors cannot ride through power dip situations. False. Our voltage range is wide, so 380 to 480, plus we have a minus 15% tolerance on that, so we could run down to 323 volts. So if the voltage dips, fan's fine. Second part of that is if the voltage does dip, it'll actually, and say that the fan powers down and is spinning down, it'll actually, when power is restored, notice what speed it's spinning at and ramp up from there. So it doesn't overdrive the motor, over torque the motor, give you current, pop fuses, pop breakers. It actually is a very smart way to ramp up, so it ramps up in a normal situation.
I've got a question about phase protection, about that range, the voltage range. What effect on the fan performance curve does that voltage difference have? So if you're running at the very bottom or the very top,
so if you're
change your max
if you're at 323, you do get some degradation in the performance, but from 380 to 480, same performance.
Okay.
And anything above 480 up into its max is going to be same performance as well. Yep. Phase protection's built in as well. So phase failure protection's built in. So what's also cool is I mentioned how it dissipates that energy with the electric brake. Here's actually a video that shows it. Now this is an axial fan. What we're simulating here is, say that this fan's on the top of a roof and there's winds and it's spinning the wrong way because the fan was off. So the fan's off, spinning the wrong way at a pretty good speed. We're going to apply the power to the fan. It's going to realize it's running the wrong way and dissipate and put on that brake to stop the fan. So the fan stops. And now if you gave it a signal to run, it ramps up from that stopped position, so it's not trying to overcome running the wrong way, and it will actually start spinning the correct way. Right, here we go. So it's not, if it's an AC fan and it's running the wrong way on a roof and you give it a command to run, it's just not going to run. We talked about BACnet and Modbus, the new controller that Q-PAC's releasing later this year, so I don't need to go into depth on that. PID controls all integrated into the electronics. By the way, the reason I chose these questions, I didn't make these up myself. It was actually on a piece of literature from a drive manufacturer about problems with EC motors. So that's where I got these myths from. This one I did make up myself. So EC motors have extremely long lead time and have to come from Europe, so that's false. This is our facility in Telford, Tennessee. Used to be true. Used to be true. This opened in October of 2022, and we're doing hundreds of thousands of EC motors out of there every year. So really has done a great job in lowering our lead times, building up the local supply chain.